Yep.
Good morning, ladies and gentlemen. Let's go ahead and do some review here on interference. Interference occurs when two or more waves are superimposed on each other.
That's right. One on top of the other.
What conditions produce constructive interference?
Y'all remember?
Constructive interference. Okay, that's when we've got our equilibrium here and here, right? And above it's a +1, and below it's a -1. And this is a +1 and a +1, so it adds up to +2, right?
That reminds me of the homework we did last night.
It should.
Let's see, that was this one right here, wasn't it?
I had a 1 + 1. That gave me 2.
Want to show them over on the board?
Are we doing that right now?
Yeah,
Oh
right.
yeah, we
Why
are.
not?
Okay. All right. So the homework last night, it said at times equals 0. It said it looks like this. We've got a block here and a block here taking up 2 of these spaces. And it was, we're saying it's a height of 1 centimeter.
Sure.
And they're moving this way and this way, each at 1 centimeter per second.
So where they're going to be in 1 second after that?
Well, 1 second after that, they're going to be moving one in together. They're going to look like this.
Yep.
Right? And then after 2 seconds, they're each going to be moving one over more, and then that's when we get that 2 centimeters, that constructive interference, them adding together.
Yep.
Okay. Now after 3 seconds, now it looks the same as this, but they're moving this way instead of moving together.
They pass through,
they pass through
each other, and then they go on, and then after 4 seconds,
it looks like this.
except going in the opposite
Yeah,
direction.
arrows are going the opposite direction. So I forget to write that down here. No, whatever.
That's
Okay.
all right.
All right, so what condition produces destructive interference? Well, bada boom. Again, equilibrium here. We have, if this is equilibrium, that's a negative one. Equilibrium is positive one. You add them together.
A trough plus a crest equals 0. -1 plus +1, and they cancel each other out.
Cancel out. Okay, 2-point sources of waves produce a pattern of constructive and destructive interference in the space around them.
We saw that with the sim yesterday, right?
Yeah, we did.
Yeah.
And a point in space may have constructive or destructive interference or anything in between.
We have a little setup here. We've got
Ooh.
2 speakers and a tone generator.
Okay, so did we decide, are we going to walk by or are we going to stand in one place and move side to side?
We could do both.
Let's do both.
Turn that thing on.
Okay.
Now, here we are right in between them, and listen closely. Now, with my ears, I can hear it getting louder and softer. Could you hear that as well? Turn that thing off!
I hope you guys can hear that. So what did you experience, Mr. Boykin?
Well, I heard it when I was closer. I only heard louder and quieter because I was in close.
Yeah.
But back here, you get remember there were more rays of constructive, and I heard more loud, and it was less obvious out here than it was up here, but I could still hear them. I hope you could as well.
Yeah, and if you guys remember that picture that we looked at the other day, I don't know what page. Oh, it's on the sticky note page. Okay, this one right here, right? So it's just like this picture right here with the 2 speakers,
Yeah.
and depending on where you stand, you're gonna get either constructive or destructive interference.
And that's what we were doing. Yeah, the 2 speakers, and we were moving across like this.
And I'm hoping you guys can hear it okay, but there's gonna be some variation in how loud it is.
Yeah.
Okay, and of course, like Boykin said, the further away you stand, the less loud it's gonna be in general because that energy has it's more thin out on that bubble, like a bubble gum being blown out, right?
It occurs to me, do you guys ever listen to the radio in a car? Have you ever pulled up to a stoplight and had the radio sound go quiet or lose it? And then you move a little bit and it comes back in? That's an example of destructive interference because the radio wave is bouncing off of something and you're getting interference.
You know what? It kind of makes me laugh a little bit though. Kids these days, they're all listening to Apple Music and Spotify on their phone. I'm like, do you guys know what the radio is? I hope so. Okay, so determine what type of interference, what type of interference is occurring at a point the length of the paths from the source to the point must be considered. And where are we gonna go? Oh yeah, book illustration. So, oh, that's over here, right? So, I mean, we could look at either one of these, right?
Yeah, and we looked at this yesterday. Where you are measured in wavelengths from each source determines whether you get constructive interference, crest and a crest, or trough and a trough, or destructive interference, half wavelength.
And if it's one wavelength over here, and then, well, if the difference between the wavelengths, is it on the next slide? If the difference between the wavelengths is it depends on the difference between the wavelengths. In fact,
Yeah.
I think I'm jumping the gun here because I think those are on the next few slides. Okay, yeah. So the path length must be determined as the number of wavelengths. So you know, we could figure out that the wavelength using this equation.
And how do you solve for wavelength? What do you got to do?
Divide by frequency.
That's easy.
Right? And the wavelength difference, this is what I was getting at. I was like, wait, hold on. The wavelength difference between the paths determines what kind of interference occurs at that point.
Yeah, and
So-
what you can do, you can either measure the difference in path in meters or whatever you're given, or you could convert it into waves and the difference in wavelengths. Ultimately, though, you need to find out what the difference in the path length between the sources and the observer is.
And so yesterday we talked about if it's constructive interference, the difference between those two path lengths is going to be a whole number, an integer, whatever the math is.
Yeah.
0, 1 wavelength, 2 wavelengths, 3 wavelengths. And for destructive, it's going to be, you know, in half increments. So half wavelength, 1.5, or 3/2, 5/2.
7
Wavelengths.
odd multiples of half.
Okay. Oh, and then let's take a look at the rest of the homework from yesterday. So
We had the one about the two speakers.
two speakers, one directly behind the other, are each generating 245 hertz sound wave. So that's actually kind of like this, right? And now me and Mr. Boykin were like, ooh, we can set it to 245 and show him, but we actually can't. We can't.
This
get
doesn't
the,
allow, this is a very coarse
Yeah.
wave generator. But here's the thing. So
So it says, what is the smallest separation distance between the speakers that will produce destructive interference as a listener standing in front of them? So
Well-
as I'm standing here, it wants to know where do these need to be, right?
well, what kind of conditions produce destructive interference?
Well, if I go back a slide here, okay? Oh, wrong way. Okay, destructive is in half or 1.5, 2.5, in the half.
So the
increments.
smallest would be half a wavelength. So what is one wavelength?
Well, let's go ahead and see how we found one. So we can find one wavelength by just doing the velocity over the frequency.
Yeah.
It gives us the velocity. We know the velocity. It gives it to us. We know the frequency. We get our answer 1.4, and then if we want it to be destructive, we just divide it by two. Cut it in half.
So that means,
So instead of being 0.7, it's is that 3.5?
well, no, you've already done that. 0.7. Because the wavelength is how much?
Oh, I'm sorry, 1.4. Instead of being 1.4 meters, it's divide that by 2, it's 0.7.
So you would have them 0.7 meters apart.
Oh,
And
you know
if you
what,
were
Boykin?
over here, yes.
When we were doing it, that actually it was making sense.
Yeah.
Yeah, because remember we held it here and it was like louder, and I was like, that doesn't make sense because we're not sure about the numbers we're getting on here. It's
Yeah.
hard to say, but it did get quieter back there, so
It
it
did.
totally worked.
Yeah. All right.
Okay. All right, so that was that one. Number 4. Oh, okay, so number 4 was just like the diagram that we had that we previously looked at. This guy over here. Okay, just like this one, except for the distances from the speakers were actually the same distance. D and D is what we're gonna call them.
Yep.
It says loudspeakers A and B, I call them S1, S2, are vibrating in phase, which just means like instead of being like do 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 do, they're do do do
Yep.
do.
Yep.
And they're playing the same tone, which has a frequency of 250 hertz. Sweet. They're set up as in that figure that we just looked at. However, the distance between them is the same, both D and D. Speed of sound is 343 meters per second in air. What is the smallest value of D such that constructive interference occurs?
Okay, so we know what this is. This is D, but how do you find the distance from this source to the observer?
Because we're the observer here. This one is cool and all, but that's not going to affect what we hear. We're hearing the speaker from this angle here. So, so how do we do this? The first thing that we did, I wrote down the frequency, wrote down the velocity, and so we wanted to be constructive frequency. We wanted to be constructive interference, excuse me. So we need to find one wavelength, whatever that is. So I did that first. 343 divided by 250 frequency. That gives me one wavelength is 1.37 meters.
Is that what you guys did, boys and girls?
It should be. If it's not, fix it.
So that means that the difference between this length, and this is the square root of, square root
2D, yeah.
It's that D should not be under the radical, but at any rate.
Oh yeah, no, I'm moving.
Okay, and so the difference between these two lengths is going to be equal to one wavelength. So.
So from there, I see. So this should be outside of that.
Yeah.
Whoops. The algebra. So from there, I took the D out in front of it like that.
As it should be.
Yeah, and then from there, there's what do they both have in common? D. So I took that out of the equation, and I got square root of 2 minus 1. And then from there, we're trying to find D, don't forget.
So you have to divide both sides by the square root of 2 minus 1.
Which is that number, and then you get 3.3. Okay, so.
Is that what y'all did, boys and girls?
So what is the smallest value of D? We're trying to figure out what the D, so that it's constructive interference. Boom, there it is.
Sweet.
Okay. Here we go. We did some facts, okay? Oh, something new. Okay, so
let's demonstrate with the things over here.
So beats.
Here's another interference phenomenon.
Okay. Should I do them like this or just like
Well,
this?
you demonstrate resonance first.
Oh, okay. So, I'm gonna go ahead and just.
You have two tuning forks. They have a frequency of about this.
And so what's happening here, and I can kind of set them up like this. Can you guys hear that?
This one is still vibrating.
Yeah. So what's happening here is I'm whacking my tuning fork, and it's creating a vibration. And it's vibrating the wood, which is then vibrating the air that's in here, creating waves, traveling through, making this wood vibrate, and in return, making the...
Do that again. Hit that one over there. Now stop it. And this one is still vibrating.
Still going.
Cool.
Okay. These have the same exact mass, although they are not perfect. They technically, vibrate at the same frequency.
And they do.
And they do. Now I'm going to go ahead and add this little number here to this, and that's going to increase the mass. And let's see what happens. Oh.
They don't have the same frequency anymore, and do that again. That sound, ladies and gentlemen, is the sound of
a beat. Let the beat drop. Okay, so beats occur when waves are slightly different frequencies. Waves of slightly different frequencies interfere with each other, and that's what we had there.
This,
right?
if some of you guys are in the band back, remember the old days when you would actually be in the band, you'd be tuning up next to each other, trying to play the same pitch. And if you and the person next to you weren't at exactly the right pitch, you hear this wah 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 sound. That's because, and what you want is you want that wah wah to go away so that the frequencies aren't different, so that they're the same.
Yeah, and that's definitely important, else it doesn't sound good, right?
Yep.
Let's see. Oscillating between constructive and destructive interference makes a wah 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 sound. And you know what? Let's go ahead and we have this tone generator over here.
While you get that, the wah part, ah, is the constructive, and the woo is the destructive. So wah 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 is oscillating between constructive and destructive interference.
Okay, so listen closely, ladies and gentlemen. We're going to start off with a very slight difference.
Wow, wow, wow. Okay.
Very subtle. Okay, now we're going to move it to 510.
Wow. So by changing the difference in the frequencies, you change the speed of the wah 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 wahs.
Oh, go more. Ugh.
Damn.
Dying. Okay.
Go back to 50. Let's do 505. See what 505 sees. All right.
I can hear that there.
And that's oscillating between constructive and destructive interference to make that sound.
Cool. Okay, and then last line. Oh no, I think the second to last line. How fast the wah 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 wahs are going are depend on how close the frequencies are.
And you had 501, 510, and 520 on one, and the farther apart the frequencies were, the faster the wah wah wahs went.
Yeah, that 500 versus 520 was like. Oh, okay. So, how could you, if someone said, I want you to calculate the beat frequency, could you do that? And you're like, yes, Miss Moore, I totally could.
Yeah.
All I have to do is the first frequency minus the second frequency, A minus B.
And once again, you might get a positive or negative answer, but the positive and negative answer really is irrelevant. The trick is how fast the wah 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 wahs are. Yeah.
And so we're going to have you guys do some homework here. Page 476, numbers 19 and number 20.
You can do this.